Okay, so reinforcement learning course. I want to apologize in advance. I had very stressful recent times because of my family is in Ukraine, and you all know that nothing good is happening there. So I'm a little distracted with all the things. So sorry if there's any mistakes in the slides or my speech is sloppy at sometimes. So yeah. Anyway, if there are any questions, feel free to ask them and we'll figure it out eventually. Okay, so just a second. I will. All right, so on this lecture, we'll be talking mostly about those 4 types of algorithms that we've briefly outlined in the previous lecture, because they are actually essential to most reinforcement learning applications and areas of research. So we'll just go into a little bit more detail into each one of those algorithms and see what they are about and like what problems that arise there and so on. So first, let's do a very short recap about what we were talking about on the last lecture. So basically, we kind of describe the system that our reinforcement learning agent lives in as the system where we have some kind of world or like real system that can exist in various states, and our reinforcement learning agent receives the state, and it has to produce some kind of an action. And the way it does it is by having some policy. And this policy is basically just a function that based on the state outputs an action, or in more general way, the distribution of different actions and with the probabilities of taking them. And in general, this policy is could be any kind of let's say complicated machinery of supervised learning, for example, or like some kind of neural network, or some decision function, decision tree, or something like that. So what's important here is that what we have is the state. We want to decide on actions, and we do this through the policy that has some parameters that we want to optimize in order to perform the best actions in the given states. And as soon as we perform these actions, we kind of take these actions and we perform them on the real system. And in this real system, we have some probability distribution over the transitions between the states given actions. So, and we described the trajectories, which are basically the sequence of pairs state action. So for the key time steps, we are given the state, and we take the action, we get another state, and so on for the key steps. And this sequence we call the probability, we call the trajectory, and the probability distribution of these trajectories can be described by the following expression obtained with a simple table, where we take the probability, the net probability of the first state, and then just multiply by the probability distribution of the actions given the current state by the transition probability of the next state given the current state and the current action. And we describe the goal of reinforcement learning as something as simple as just optimizing the parameters of our policy, the parameters theta here, and we want to maximize a certain expression. And this expression is basically the estimated reward. So basically the sum of the one-step rewards for a certain trajectory. And we take the estimation over the trajectories drawn from the probability distribution of these trajectories. And we, yes.
Sorry, excuse me, may I ask a clarification question regarding the pi theta? Is it the probability of AT given ST?
Yeah, so basically this is, yes, it could be seen as, yes, it's a probability of AT given ST.
Thank you so much.
Distribution, yeah. Yeah. So basically, we had a very important conclusion in the previous lecture that basically, if we rewrite this estimated common reward, if we just take the sum, the estimated sum over the sum, if we sum it in another direction, we can rewrite it like this. So we sum over the time steps instead of different trajectories. And for each time step, we just take individual pairs of state and action, and we can sum the rewards and calculate the estimated reward per state and action drawn from some probability distribution of these pairs, state and action pairs. So, and then we outlined the basic anatomy of a reinforcement learning algorithm as a very simple three-way scheme. So first we generate the samples by running our policy. So we take the original state, we take an action according to our policy, end up in the second state. Based on that, we again apply our policy with the second action, and so on. Within some infinite or finite time horizon, we generate the samples, we generate the trajectories. And on the initial steps of the algorithm, this could be some arbitrary policy, for example, random policy. And then with these generated samples, generated trajectories, we estimate the rewards, or we fit some kind of a model that describes our rewards, and we improve the policy based on that information. So basically, we look, intuitively, we look at the trajectories that improve the rewards, and we try to adjust our policy so that it would benefit mostly and prefer those actions that maximize the reward. So first, we will start with model-based raw algorithms, and this is a very big family of raw algorithms. And the one common thing between them is that we try to learn the probability distribution for the next state given the current state and current action. And here we can use different terms. So we can use this as a transition probabilities, talking about market decision process, states, and the transition probabilities given the state and action for the next state. Often the term transition dynamics is also used, and also dynamics, just dynamics. And for clarity and simplicity, we'll just use the dynamics in this lecture. We'll try to stick to that. So basically, the model-based raw algorithms, they try to describe kind of the physical system that they interact with by modeling the dynamics of the system. And then by observing some trajectories and trying to model these dynamics, we then can use different algorithms to improve the policy based on the known dynamics. And in the previous lecture, we just left aside, we said there are like a few options to do that. And here we will actually describe a couple of them. So first, assume like what shall we do if we already know the dynamics? So go just directly to those few options. So first, let us introduce two different concepts of the reinforcement learning, or in general any system interacting with the real world based on the state and action concept. So first, something that we've already discussed a lot on the previous lecture is a typical reinforcement learning agent. So the agent basically obtains this current state of the system, and then it runs its policy, and given the state, it outputs some action. And it outputs the action usually stochastically from some probability distribution. So given the current state, we come up with an action. And then it feeds this action to the system, so it performs the action, and this action changes the state of the system, and then we get the next state, and so on, and we repeat this in a cyclic manner. And this is usually referred to as a stochastic closed loop system. And closed loop because we constantly get that feedback from the real system. If you think about it, in many systems, or like even if we take some live examples, we don't always do that. So for example, if you plan to, for example, cross your room and go to the door, for example, you plan some actions how you will do that. And you usually, like in your mind, you don't really adjust it every millisecond, replanning the entire route. So, and the same if you're looking for something, you plan your route with the Google Maps, for example, and then you perform this action or sequence of actions, for example, go somewhere, turn somewhere, and so on. And then after a while, if you look and you find yourself not where you wanted, you kind of revisit that and perform a sequence of actions again. And this concept would be probably most familiar to those of you who are already familiar with the control theory. Is basically a stochastic open loop system. So, and in this case, we basically what we get is just the first state. And then given the state, we have to think of a sequence of actions already and submit those sequence of actions to the system. And we don't really keep iterating that. So usually this open loop system, the AI agent just has to have some system, for example, a neural network that gives that receives the state and then outputs the sequence of action. But it doesn't go this in a cyclic manner. So it just wants to do this based on every given state, output the sequence of action. And now here, I skipped this because we've already seen it on the previous slides. So again, the probability of a trajectory in the case of the closed loop system can be expressed again like this: net probability of the first state, and then the product of the distribution of the actions given the states according to our policy, and then the dynamics. And then we want to basically find the best policy by optimizing the expected reward. And in the open loop system, it's slightly different because now we don't really have the sequence of state action. It's more like we have a sequence of actions, and on this we condition the sequence of state that we will end up executing these actions. And in this case, it would be simply given the first state, we can net probability of the first state, and then just given our iteratively state and action pair at each time point, we get the probability of the next state. So this is the dynamics. So, and here the difference you can see is that here we don't have the policy at all. And this kind of, again, for this kind of system, we again want to maximize the reward, and the reward in this case would be just if we take again this sequence of actions. We don't know the states that we're going through, we know just the first state, but in principle, the reward would be again the sum of the rewards per state action pair. And to solve this, so for the AI agents to be able to output the sequence of actions, this would be some kind of an optimization problem which maximizes the reward over different set of actions. And of course, just this problem separately is not enough to describe this state because we have the transition dynamics. So this optimization or maximization problem would be constrained because here the actions and the state are not just independent. So we have to optimize the reward of the trajectories over different sequences of actions such that each next state is a certain function of the state and action. And function here is the same as the dynamics, just a short way to express it. So in here would be basically very concisely express dynamics. So given the state and action pair, we get the next state. So in short, again, in this open loop system, we would just need, we don't have any policy in this equation, but we do need to solve this problem. So we need to optimize or maximize the relative reward over different trajectories, where trajectories in this case is just a sequence of actions. So how to solve the optimization problem in general? That's a very good question, and I'm pretty sure you know already different methods to do that. But in this context, there are a few commonly used approaches. So the most trivial approach would be just kind of randomly sampling different sets of actions, and then for each set of actions, we evaluate the cumulative reward, and here we just, for conciseness, we call it J, given the sequence of actions, and then we want to basically, if we express the sequence of actions as a capital, we just want to solve this problem. And you can do, again, just every time you can just try different actions and select the one with the best reward. That's very simple, and it actually works quite well in low dimensions. So the algorithm here would be just take some distribution, and it could be, for example, uniform distribution, so just random sampling. We pick different, like a set of n different sets of actions. So each set of actions is a trajectory, and then we pick n different trajectories from some distribution, and then just take the maximum. So very trivial, no tricks. Slightly more kind of adaptive method is a cross-entropy method. And it starts similarly. So we have some distribution. Now we don't say it's uniform, but let's say we have some distribution. It could be uniform at the beginning. Then we sample different vectors or different sets of actions from it, evaluate rewards for each of them, and then not just take the one and output as a result, but here we take a small number of the sample trajectories which have the highest reward or highest J value, and we'll call them elites. And then we refit the distribution to these elites. And this would be kind of an adaptive method because we will start from random sets of actions, and then we will look at ones that give the best reward, and we kind of try to fit or overfit into those. So we try to adapt our distribution so that it represents the best sequences of actions. And this method works much better than random shooting, obviously. And more of like a state-of-the-art method. Again, we always know the dynamics. So currently, we're just talking about a case where we know all the transitions, so we always know the dynamics, so we know how, given the state in action, get the next state. So the most common, or like one of the common approaches is the Monte Carlo tree search. And in a simple formulation, for example, for discrete systems where we have discrete set of actions, discrete set of states, we just start from the original state, and we start creating the tree. And here we would just take some first action. Since we know the dynamics, we know which state we end up with. And then we do the same. We just take, for example, a random action, or again, the action given some known distribution. We end up in the next state. And then after reaching certain depth, we would just run some default policy. And with that, we obtain the reward for that state. And just remember the value of the reward in this state. And then we, again, we go up to the root again and tell all these states that from this state, we can actually get this kind of reward eventually. And then we repeat this, and then we'll take some different actions. And there are plenty of little tricks how you can improve the Monte Carlo tree search. But that's, again, the method itself is outside of the scope of this course because it's a pretty common method in general optimization. So in general, for those of you who are familiar with the control theory, you know that there is such thing as a trajectory optimization. And again, that's something from the control that very well established, and doesn't really have a direct connection to reinforcement learning. It was created much earlier than reinforcement learning itself. But basically, what do you need to do in the trajectory optimization? Well, it's similar to what we want from the reinforcement learning. So we want to minimize the cost of going through a sequence of states given the sequence of actions. And here the terms cost, state X, and action U is these terms or this notation is taken from the control theory. This is how it's pretty commonly described there. And again, in the trajectory optimization, you have to solve the constraint optimization problem by minimizing the cumulative cost. And it's constrained by the fact that every next state is, again, is a subject of some kind of a dynamic that given the previous state and action gives the next state. And if we unroll this expression, we'll get something like this. So if we directly put, instead of x2, we put f of x1 u1, and then instead of x3, we put f of x2 u2, and this would be the expression if you unroll x2, and so on. So it's a long and complicated expression, but here it's basically, it's kind of the same formula, but now you have to optimize this, just having f in mind. F, again, is a dynamic, so it's something that we currently supposedly know. And to solve this problem, it's pretty trivial. You have the cost, and again, the cost is something that is also available. It's could be seen as a negative reward with the analogy with reinforcement learning. And basically, to solve this optimization problem, you can use any gradient descent approach. And to solve it, you basically only need the derivatives of this f, the dynamics, the derivatives respect to the states and actions, and the same with the cost. And again, since we always know the cost for reward functions, this is something that is always given, or that we engineer it. And the dynamics is is currently known, so we assume that we know the dynamics. So this will be no problem for us. And actually, in the control theory, for convenience, it's usually seen as the same state optimization problem, but with respect to a set of actions and set of states. So this is just how it's formulated there. So it just it doesn't really add much, because here we have basically the transition given the state and action, the new state. But in general, it's the mathematical machinery is such that it's easier to formulate like this. But here it's not really that important. So, and there is a common control example how this is done, and it's basically done by approximating the dynamics as some linear function given the states and an action, given the current state and an action, and the cost function is the quadratic function. So again, given the state and an action, it's kind of a quadratic function because we have this multiplication of this vector, and yeah, one half tells you that it's like half of the square plus vector itself multiplied by some parameter. And this formulation usually makes it much easier to solve this optimization problem. And just to tell you that it's actually not this linear quadratic regulator approach is not something that's only applicable to the systems with linear dynamics, because any system with also non-linear dynamics, you can any arbitrary function that represents the dynamics, you can always express it by unrolling the Taylor series. So you take it around some x hat u hat point, and you take the value at that point, and then the first derivative gradient. And for the cost function, you can do the same in a quadratic sense. So you take first three members of the Taylor series. So just want to make sure that you know about this, because you'll likely find this LQR regulatory in many places, and it's important to know that it's something that's in the name, linear quadratic, but it's just the expression, and it doesn't limit you to the linear systems with linear dynamics. So again, if we know the dynamics, basically there is plenty of methods from optimization theory how you can solve it. So, and then you don't have any explicit policy, so you basically just policies to solve the optimization problem. But this is if we know the dynamics, and the question is, how do we know the dynamics? And here. Let me see if we so I think I've missed one slide here, but basically doesn't matter, because the answer to the question is pretty simple. So how do we know the dynamics? And basically the question lies in this, the answer lies in this scheme. So when we generate the samples, we basically generate the trajectories, and the trajectory is a sequence of state action, state action, state action. And basically, if we represent the dynamics with some kind of function representation, and it could be, for example, a neural network, which inputs the states and outputs the actions, or sorry, given the state and an action, outputs the next state. We can just take our trajectories and feed that data to it. So we just take the tuples, state, action, next state, and then we just fit any, for example, neural network to give us the output based on the state and action, current state and current action, give us the output to the next state. And so the thing is that here, these two boxes are not really connected. So basically here we take the samples that we generated. So for example, on the previous step, we solved the optimization problem, and now we come up with a sequence of actions. And then we take that from the system, we take for example, the current model, we estimate the sequence of states, sequence of actions, and then we fit our model to that. So, this is basically, this part can be done separately in the form of supervised learning. So now let's go to the value function methods. So basically, the model-based methods is some people say it's not even the reinforcement learning, because basically it's just taking two separate parts. So one would just predict the dynamics, another one just solves the optimization problem. So from now on, it's more like involved reinforcement learning algorithms. So with the value function methods, if you remember from the previous lecture, the idea was that we again generate the samples, and here we estimate the returns. And here we don't really talk about knowing the dynamics or not knowing the dynamics. We just say that we represent the overall return in the form of value function or Q function, and then we kind of update our estimate of how these functions look like. And then given the samples, we can estimate the rewards, and then try different actions from the current state and select, for example, the one that gives the best reward. That would be our policy. So let's do it in a bit more detail. So from the previous lecture, you probably remember that we had these two types of value functions. So one is the Q function, which given the current state and the current action, and again, it's given some kind of policies that we currently have, it estimates the total reward from taking action A from the time point at st, and then we keep following our policy. So basically, we are given the current state, and a current action. And the Q function tells us what's the reward would be if we start on the state, take this action, and then just follow our policy, what the estimated reward would be. And the value function is pretty similar. The only difference is that instead of saying that making the action at the time t as a parameter, we just say that, okay, we also take that from our policy. So we just start from our state and then just follow our policy and see what's the estimated reward we did. So again, they are quite similar, and there is like a very clear expression between them. Basically, this the value function would be the estimated value of the Q function if the next action is just drawn from our policy. So, and another type of value function that we'll be using is this A function, which is the advantage function. So the advantage function is, again, very simple. It's just the difference between the Q function and the value function. It's important to understand what it is. So basically, again, it takes some current state and current action, and then based on this, it outputs. It looks at the Q function, so it knows the estimated reward that we take that we get from the state if we take the action AT, and it subtracts the value function. And value function is some kind of an average of all the actions that we draw from our policy, given the state ST. So basically, this difference tells us how much better state the action AT is compared to the average kind of action taken from our current policy. And again, if you can just rewrite it by unrolling this expression for Q. So again, the Q is just sum of estimated rewards of the state action pairs. So if we take, for example, just first SA, first state action pair, we just take this reward because we know state, we know action. So here it's pretty clear. And then from the next state, it will be just the estimated value function of the next state. Because again, in the Q function, we know which action we take. That's the parameter that we have here. So this would be something that we know. But from the next state, so here it's described as S prime, it would all be following just the policy, and just following the policy is the value function. And again, here we take the estimate of this value function because, again, for example, our the next state could be some kind of a probability distribution, and that's always what we have. So we describe the original dynamics as the probability distribution of the next state given the current state, the current action. So here we take the estimate of the value function given that probability distribution. And here we just subtract the value function of the S. So that would be an alternative expression for an advantage function. And if you think about it, for example, what happens if our time horizon is infinite? And last time we described that. But in this case, if we write an advantage function like this, here would be also some kind of infinite horizon. Or what's worse, if we have some kind of a cyclic system where we just cycle through the states, this expression would be unviable because here there would be some kind of repetitive infinite terms. And this is usually mitigated, and we'll probably motivate it a bit later, by putting this gamma coefficient. This is often called the discount factor. And this is some factor that's between 0 and 1 that just discounts this estimated value function from the next state. And this is done just to remove this, again, the problem with the infinite horizons or cyclic systems. And in more humane way of explaining what it is basically slightly prioritizing the short-term rewards than long-term rewards, because again, long-term rewards could be infinite, or it could be we would end up in a cycling. It also would be infinite, and this just solves that problem. And again, it shouldn't be like small. In practice, values very close to one work well. It's usually less than one to avoid infinite problems. So, and in the following slides, we'll use a lot of this Q function, value function, advantage functions, just by using different expressions that interconnect them with each other. And we'll see that in some cases, one is useful, another one is not, even though the relation between these two values is pretty simple, but there's a lot of hidden interesting math in there. So basically, a typical value-based method works as the following. So again, we remember this scheme, but in the green box here, we fit our current estimate of one of these functions. And then we use that to improve the policy, and we usually do this via policy iteration algorithm. And policy iteration algorithm is, well, probably one of the simplest algorithms. It has just two steps. So first step is evaluate current advantage function, given for example, the state and action. And then we set the policy to the new policy that somehow updates, somehow prioritizes the actions with the higher advantage function. And usually this updated policy is the following. Again, we saw it before, so it's a very trivial policy. So basically, we take different actions. So basically, over different trajectories, we take the one that maximizes the advantage function of the state action, and we just enumerate, given the state, we enumerate different possible actions, and we take the one that maximizes the advantage function, so the one which is the best, and it's also the best compared to the average, of course, and we say that in the state ST, we would take that one action, AT, with the probability 1. And we won't take any other actions. So the probability distribution given the state would be pretty simple. It would be discrete. It would be just 1 for AT, which maximizes the advantage function, and 0 otherwise. So this is a very trivial policy. And here, if we, again, look at the evaluation part, so this step is pretty clear, right? So we just the advantage function, the previous step, see which action of the ones that we can try maximizes it, and update our policy to prioritize that one. And then we again, is given the new updated policy on the next step, we again do the same thing. And the question is here how to evaluate this function. Just to remind that this advantage function has the following expression. So here we again talk interchangeably between advantage function, Q function, value function, and here we'll be, like, if you look at this expression, you can see that we can actually express advantage function via the value function. So here on the next slide, we'll be talking about how to evaluate the value function. Sorry, just. Yeah, sorry. So basically, the question again is how to evaluate this value function. So for simplicity, let's look at this trivialization of our system. So let's assume that we know the dynamics, we know the transition probabilities, and that both the state space and action space are discrete and pretty small. So some, let's say, trivial board game. And here's, for example, let's imagine that we have 16 states in a grid 4, so we can be in one of the 16 cells. And we have 4 actions, so we can go left, right, both up and down. And of course, in some cases, for example, in this one, the action up would have normally zero probability. So the transition given, for example, from this state with the action up, the probability would be zero. But okay, so we can observe everything, so we know the states, we have small number of actions, and we can also store, basically, if the number of states and actions is small, we can actually just represent this function in a table. So, and the table would be just like 16 items by the number of states. So the value function is defined on a state. And here we'll be talking about kind of a tabular reinforcement learning. So tabular means that we just represent it in a table, or just like very expressive form, just literally just writing value function value for each state. So then the question is how to evaluate. And the idea here is that is to use dynamic programming. And I'm sure most of you are familiar with dynamic programming, but the idea is that if you have the information in some states, then you look at where you can go, or like which states you came from, and then you kind of recursively represent the value of the current state by the previous state. And here it's pretty similar. So it's basically if we have some, let's imagine that we have some current estimation of the value function, and just like some table with some values, like 0.2, 0.3, 0.4, and so on. Then if we, for example, got new trajectories, we got new data, then we can actually update our value function. And here, basically, you can see that this expression is basically the advantage function expression, but without minus value function part. So this would be like the expression of advantage function plus value function, which is the Q function. And the estimated value of the Q function over the probability distribution of actions given the current state is the value function. So this is just the simple recursive expression for value function, the current state S, via value function at some different state S. And again, so if we have a current estimate, we can get these values directly from this table, and we can update some new point in this table. So, and again, you can look at this, for example, just by having some estimate, current estimate of the value function, and then using that to update the estimate in some other state. And again, otherwise, you can also just try this for every state, this kind of activation, and then say that at the convergence point, these value functions here and these here, the current estimate and kind of the next estimate, they should be the same. So this written for every state would be just a system of linear equations that you can solve. But again, this is all kind of talking for a very small discrete sense of state space and action space. But again, so here we have the kind of, we know how to evaluate this value function. And from value function, again, via this kind of an expression, we can get the advantage function, and again, try different actions, see which one maximizes the advantage function, take that and update our policy to always take that. So, and again, so this would be the same. So basically, we can update again the value function just by using our policy and showing just by taking action which corresponds to our policy. So this simple policy iteration algorithm that we were talking about, we can now just augment it with the policy evaluation part, where we do these updates, and this arrow shows that we just repeat this several times. And here, the advantage function that we use So the question is there maybe a way to simplify this computation? And the trick that is used here, it's called like a maximum or argmax trick, is basically, if we look at what we do here, is we have this advantage function, and we, to update our policy, we have to take the argmax given some actions that we tried. And again, since the value function doesn't depend on the action, this argmax advantage function is essentially the argmax of the Q function. And again, by taking this argmax, so by taking the action, we update our policy. But the question is, do we actually need to directly update our policy and know this action? And the answer is really no, because what we can do is, like, if we look at the bootstrap update of value function, let's look at here where we use the policy. And the only place where we use the policy is basically here, by taking different actions, or not the different actions, but rather the action that our policy gives us. And this would be this argmax, but also this, also here. And the thing is that usually we don't really need to express this itself, but basically we can just use, instead of using argmax and putting it in these formulas, we can just use the actual max values here. So instead of, for example, taking expressing this as taking states of probability of the states given the current state and the action given by the current state, which would be this argmax, we just directly go to the take that action, and in the expression for the value function, we just use these argmax values for Q or for A. And so, like, to simplify this in a formula way, we can just rewrite it like this. So basically, here we will be operating with the Q function as on the previous slide, because it's the advantage function here. It's the same action maximize advantage function as the Q function, because the value function part doesn't depend on action. So here we'll be mostly using the Q value, Q function. So here will be, again, the update the Q function based on the current values, and again, the V function is itself the estimated value of the Q function, so we can express this by current estimate of the Q function. And then we update all the value functions here that will be used in the next step. We just use this as the maximum Q function of the different actions. So here we don't use the argmax, so we directly update the value function in our table, as you said, we have a table, and we just update that during our current Q function estimate, and the Q function estimate itself is also updated via the value functions, which we all know like directly expressed in the tabular form. So, and so the scheme of this kind of Q learning algorithm would be, so again, we generate the samples, then we update our Q function estimate, and the next step, we improve the policy by just we don't really express the policy directly, but we just update the value functions that depend on this policy directly from the Q function estimates on the previous step. So here we don't have the explicit policy, but just like we close the loop just in terms of Q functions and value functions. And this type of algorithm could be updated to a so-called fitted value iteration algorithm. And this is basically when we don't have a very small table that we can express all the value functions values, is basically, for example, expressing value function as a neural network. The state outputs some scalar value of the value function. And this would be more suitable, for example, for continuous distributions, because then you can basically plug the continuous input in the neural network. And this part could be simply optimized with a very simple loss, which is based on basically the current estimate of the value function from this network, and its difference or deviation from the what we wanted to update with, so according to the second step. So we want to set this v value to the maximum of the Q functions taken, given different actions taken, but we don't have we cannot really update the function which is not in tabular form but rather in neural network form. So we just do this by actually optimizing it with this loss, or backpropagating the deviation from the ground truth. And this we will call the ground truth. And we keep this updating. So basically the algorithm will be updated like this. So here for clarity, we don't write the Q function because it's some kind of surrogate that we base on the estimated value functions from our neural network. And again, we basically optimize, we try to take different actions. We estimate this kind of Q function value, take the maximum, and then we look at the current suggestion by the neural network, what it says about value function, and then basically optimize with respect to the parameters of the, let's say, neural network with this in mind. So we try to minimize the discrepancy. And then we repeat this again and again, and eventually it might converge. So, but again, so all of this is basically implying that we know the dynamics. Because by knowing the dynamics, we know what this next state is. So this is the current repeated value iteration algorithm that we just discussed. And again, if you look at where we use the dynamics, as we just said, so first place is basically looking at what the next state is. So to know that we need to know the dynamics. Also, we need to know some distribution of the probabilities to get the estimated value. But also implicitly, we say that we know the dynamics because we try different actions. So by trying different actions, it implies that we should know the dynamics, because we can kind of simulate what happens if we take this action. So basically, then we can. So the question is how to solve this, and basically we can approximate this estimated value of the value function for the next states, just like this. So by maximizing the Q function of all the possible next states, given some distribution of actions. So the question is how to do that. And to answer that, we first need to understand where originally this, to trace back, where did all this come from? And originally, again, it came from the simple policy iteration algorithm, where we talked about Q functions and evaluate Q functions by literally getting estimated rewards and take the action that maximizes this reward. And then we did the policy evaluation update. So we replaced this step with this step, where we expressed everything in terms of value function and did this bootstrap update. So again, here we have this part where we kind of need the dynamics. So literally this part describes the dynamics. And if we look at the kind of if we rewrite the same with the Q function, so if we try to update not the value function but Q function, which is defined both in the state and in action, it will be a similar equation. So here it will be the same, and the difference would be that instead of taking the action that's given by the policy, we just take an action that's given by the variable. So here the pi of s would be replaced with the action variable. So, and do we really need to know this probability distribution? And the answer is that not, because basically although the value function and the Q function they look pretty similar. So one is just like by taking the estimated value of another one by taking different actions. But here it's very important that in the value function case, basically the whole expression depends on our policy. And here it kind of implicitly depends on our policy because our policy decided the trajectories that we got, you remember in the orange box. But in fact, we don't really need to know the policy itself here because we got the trajectory and we know what are the actions that we took. So, and the answer to this is basically we just have to sample these tuples. We have to sample tuples of the state, action, and the next state, and just by sampling those from basically taking the trajectories that we generated on the previous step, they are generated according to our policy, which again, the Q function expression shouldn't really know anything about it. But since we got them from that distribution, by running our policy, we can just sample or like take the subset or the entire set of these trajectories and just take these tuples from the state, action, and next state. And then just by feeding these samples into this expression, we'll be just doing the following. So we just take some tuples and take this. So there will be no estimated value because we just did the Monte Carlo approach. We just sampled them, and then we just look at the state, just update the value, need the values of the Q function given the next state and an action. So by doing this, it's a very subtle but very important moment that we can go to like from the value function to the Q function and not worry about the policy here, or we don't really know to express the dynamic directly. So it's kind of implicitly described in the trajectories that we got. And here we can kind of feed that information just by sampling the tuples along the trajectories. So basically by working with the Q functions, this is often known as a Q iteration algorithm. So as we here said, we just collect the data sets with the trajectories using some policy that we had on the previous step, or originally could be on the first step, random policy. And then we collect this data set, state, action, next state, and also the reward on top. So on the next step, we again do this as before. We feed this surrogate, which is basically the maximum Q functions over trying different actions. So we update it with the reward and maximum Q value of the state and action pairs. And usually we do this, we approximate Q function as a neural network. It's again a kind of the easiest way probably to plug in the learning part into the algorithm, just by representing this as a neural network, taking, for example, state and action and outputting the value of the Q function. Or in practice, usually you just feed the state, and then we have kind of as in the Bayesian classifier, the set of probability distribution over different like actions and the Q values. And then again, we did this, we calculated this kind of, instead of argmax and writing the policy directly, we just did this max trick. So we just take the maximum value here, and then we kind of estimate what our neural network says, and then just like propagate this to optimize, basically fit the Q network. And again, we repeat this. And the important part here is that we can repeat this with the same collected data set. So that means that if we collected some set of trajectories, we can keep running this, and we can therefore basically fit the Q function. So for example, train the network, we just use the Q function, and then we can basically, when we need to output the action, we can write the policy explicitly, basically doing the argmax of the Q function based on the Q function values outputted by our trained network. And this part, so again, and after you did this, for example, you improved your Q function estimator, you can use that to basically draw new trajectories by, again, writing the policy explicitly. We collect new trajectories and then repeat this whole process again. And you can say that kind of the internal part of this algorithm is basically off policy, because again, first we don't even ever represent the policy here, and we use the same set of trajectories. And basically we can, since it has like two different loops, we can take this, for example, to one of the extremes and update and get the trajectories every single step. So we basically take not even the whole trajectory, but even very short. We just take one action. So we get a state, we take a new action, we get a new state, get basically all this information as a training data, and then we do just one single update. And again, we try different actions. The trained Q network gives us Q functions, and then we get basically, since we know the next state from the training data, we just plug next state and some different new actions into the Q network. It gets some value, and then we can backpropagate, and basically it's one step of the gradient descent. So we just base it on one single state and action pair, and then we repeat this again. This part is called the online Q iteration algorithm, which basically implies that, yeah, we take the new data as often as it is. And so again, here we don't really express the policy in the process of training. So we just get away with expressing Q function as a network. But when we need to, for example, generate trajectories, we do or express our policy as the following. So again, we take different random or different actions, estimate the Q function for the current state in this action, take the maximum, and take the action that maximizes this expression. But in practice, this doesn't really work that well, because, well, first of all, we have, well, if, for example, in the beginning of the training of your algorithm, you're like, if you just, let's say, initialize the network with some random weights, it can really push for something wrong. And then you will keep digging into this wrong part more and more. And then your Q network will never really converge to meaningful values. And your policy will always be bad because it will completely miss something good. And to kind of adjust to this a little bit, you can do it like a leaky style. So you can leak some probability into other basically into other actions that you tried. They didn't maximize the Q function, but you can still give them some chance to try that. And this part is more flexible. And again, even more flexible would be just taking, like, expressing the policy as the probability distribution, taking it into account all the Q functions that you got for different tried actions, and then, for example, draw it from, let's say, like a Boltzmann type distribution. So this would have even more sense because, again, you don't directly take the very best one. You still have a chance to take the worst one because maybe your Q function is not perfect yet, and this will always be the case. But also you range them according to the Q function. So there is kind of balance between how you trust your Q function and how you don't trust it. So with this, these two methods, so model-based reinforcement learning algorithms and value-based algorithms, basically what we saw is we had some learning models. So in terms of, for example, model-based reinforcement learning, we had the model that represents dynamics. And here, in the case of value function methods, we had the model that represents the Q function. And in the place of policy, we had a very simple, or like, let's say, trivial policy. It was like if-else style. So basically, if this action maximizes the policy, maximizes the Q function, then we take it. For example, in terms of dynamics, we also we just try different, like in random shooting, we try different actions, or we do like a simple optimization algorithm. So, but in reality, you would like to have to be your policy more adjustable, because if you fix it, then you're kind of constrained to what your policy tells you, as we seen on the previous slide. Like if you constrain it too much, you can lose the good actions, especially in the beginning of the training. And there are basically many problems if your policy is not has this very simple expression, and it's kind of very, very fixed and biased. So what if we want our policy to be unbiased? Well, the simple answer is policy gradients. So, and this is the third type of algorithms that we kind of outlined on the previous lecture, was that basically in the policy gradients, we just evaluate the returns that we got from the trajectories. So no Q functions, we, let's say, just blindly took the states and actions that we did, looked at the returns, and then now we want to kind of tell our policy that the trajectories that we had in the previous step with the good rewards or good returns, they should be preferred, and the ones that had bad returns or bad rewards, they should be disfavored. And in a simple expression, this would be something like this. So the parameters of our policy would be updated with some kind of a gradient of estimated reward, so, in respect to the parameters. So this is very generally written, and we actually need to take a bit deeper look into this, because it's currently it's very vague. So the question is how to evaluate the returns in the first place. So as I've said, the goal of our reinforcement is to maximize the expected sum of rewards along the trajectories that are sampled from our current probability distribution of trajectories, which in turn depends on our policy, and this is expressed by the theta subscript. So for simplicity, we'll just again write this as a J of theta. And we can again imagine it like this. So we, on the previous state, in the previous iteration, we just sampled some trajectories in this orange box. And now we kind of range them according to the rewards. So the thing is that by doing this, like sampling trajectories and doing basically looking at the rewards, we don't really do the full expectation here. So we don't really have the expectation, because we do basically literally just sampling. And that means that if we sample n trajectories, then basically we approximate this estimated reward just by averaging over different trajectories the reward along one trajectory. And again, here what's important is that we have this M trajectory sampled from the current policy. So, and now, okay, so we evaluated rewards or returns by just sampling from the current policy. How to differentiate it? Well, again, let's just rewrite this reward trajectory as R of tau. And we kind of want to maximize this function, which originally is the estimated value of the returns. And again, so this would be just a short expression, the rewards along the trajectory. And again, so here we write strictly equals to, and again, here we work with the continuous case. So say that we have a continuous space of trajectories, which is just which is always nicer because it's kind of a generalization over discrete spaces. And here it actually doesn't take much effort to replace discrete with the continuous. So this, so we want to maximize this, and we can rewrite the estimation basically as the product of the probability of certain trajectory with its reward, and this is all over the space of different trajectories. And to make sense of this equation or this expression, we'll use one simple trick that's used a lot actually in the mathematical operations here in reinforcement learning. Is something that everyone knows. Is that the differential logarithm is actually the differential x divided by x. And here if we replace x with this the theta of tau, so basically the probability distribution of trajectories, we get this. So, and we replace the differential with the gradient. So here the gradient of the logarithm of this probability distribution trajectories is the gradient of the probabilities divided by the probabilities themselves. And again, by multiplying each part by d theta of tau, we get this expression. And yeah, so now how do we differentiate this? So because in order to basically do this R max, we need to backpropagate the gradients of this expression, so gradients of J. So now if we write the gradient of J, this is essentially the same. It's linear operator, so we can put it under the integral. So it's integral of the gradient P R of tau d tau. And now we can replace this gradient P tau, which is also here. We can replace it with this a little bit more sophisticated expression, which is P tau itself multiplied by the gradient of its logarithm. So here we just use this trivial expression. And now if we look at this, we can actually see what is actually this probability and reward. So we can see that it's been already here, and what it actually is if we like do this derivation in the opposite direction. So we look what this integral is, and essentially this integral is the estimated value of the gradient grad log p multiplied by the rewards. So basically here the gradient would be something similar to this expression. We just had to multiply the reward function by this gradient log p, where p is the probability distribution of our trajectory. And then again, so we have to solve this. So we have to maximize the arguments of our policy, to maximize the j, where j is expected return, or is expected reward, and then the gradient we express like this. Now let's actually write out what this probability here, and this is something that we saw on the first slide, which is basically the probability of the trajectory is this, the net probability of the first state, and then product of the probabilities of the next action AT given ST by the dynamics of transition probability. So this is our p theta tau, If we figure out tau is the probability of having this trajectory. And if we just put the log in front of each of the parts here, this product will turn into the sum. And here, look, so here we really need the gradient. So, and if we write this out, so basically the gradient of this entire sum, look which parts actually, since this is the gradient in respect to the parameters of our policy, let's see which parts are actually dependent on it. We can see that the first part is something constant to the system. It doesn't depend on us at all. So we can remove it. And the same with the dynamics. So dynamics is some intrinsic part of the system, and it's here we don't really like, it's not like in model-based learning that we do some like approximation. It's just like what it is. So it doesn't really depend on our model. It doesn't have the parameters data. It's just the intrinsic dynamics of the system. So we can remove it as well. So and then we end up with this simpler equation. And if we again put it right here in this equation and then write out the taus and or like the rewards of the tau as the sum of the rewards for each step. So this is the gradient of our expected reward. So it's estimated value of this huge expression. So how do we do? So now we knew how to differentiate it. We put the expression for the estimated reward. How to actually evaluate this? And basically, again, so the simple way is approximate the estimated value as by sampling. So as we did before, we approximated the estimated reward as the average over n samples. So similarly, like if we do the same approach for this gradient, it would be the same. It would be 1 over n sum for n trajectories, and for each trajectory we would have this sum of grad log pi, where pi is our policy, and multiplied by this total reward over a trajectory. And again, if we look at this this gradient, we can see where, like, when we want to evaluate the policy gradient, we see where each part comes from. So, for example, this part would be just obtained from generating samples, basically running our policy n times, generating n trajectories. Then the return estimation or reward estimation is here. So basically, for our trajectories, we calculate the reward. And then here would be the part which is responsible for improving the policy. And then again, so this gradient would be fed into our policy, whatever model it is. It would be, again, a neural network. So we just fit our gradient there and update. So, and basically here already you can see that every time we update the policy, we need to new trajectories drawn from the new policy. So it kind of already gives you a hint that it's probably an on policy algorithm, but we'll talk about it in a few slides. So again, the basic policy gradient algorithm is rather simple. So we just sample the trajectories from our policy. So we run the policy several times in the simulator, for example, or in the real system. And then basically estimating or evaluating this gradient of rewards as this equation. So we have the rewards here, and we have our policy expressed somehow, and then we do the grad log here of the policy. And this policy would also have some kind of expression. And then we feed these gradients back into the parameters of our policy. So to make sense of how to compute this, like one of the trivial ways to express the policy would be the Gaussian policy. So again, instead, like in contrast to what we had in the Q function methods, for example, instead of saying that for the current state st, we would have one action AT that we take with probability 1. Here it would be some kind of distribution. So it would be some multivariate normal distribution with a mean that is modeled by the neural network given the state, and some variance. Could be same, could be also learned with the neural network. And then again, you can, for example, when you have like closed expression like this, we can calculate the logarithm of this, and then they calculate the gradient logarithm of the policy expression like this, and then we basically calculate this given our model for this f, which could be again a neural network. So the question is, does it work well in this setting? And the answer is in general no, because there are plenty of ways how to improve it. I will probably touch just a few of them since our time is almost running out. So one important thing is, let's imagine that we have this the expression that we do it now, and so we draw some limited finite number of trajectories samples. And here we have basically some probability distribution of different trajectories given by our policy. So let's say it would not be like one-dimensional, of course, because the policy is like a lot of states and actions in consequent, but it would be some kind of distribution. And imagine that we, on the previous step, using this policy, we took 3 samples, and 2 of them had like small reward, and 1 of them had a very big negative reward. So when we do this cycle where we evaluate the rewards, so we got these rewards, and then the next step where we have to calculate gradients, we will obviously disfavor these trajectories. So since it's negative reward, it would be like completely disregarded and everything gets around it. But in contrast, these two would be more favored. So our distribution would shift to something like this. Now what happens? So here we remember that we got this. So what happens if we instead raise all rewards values by some constant? We would get something like this. So we would get 2 trajectories with a big reward and 1 trajectory with, like, say, twice more reward. And then you can see that if you plug it here in this equation, this trajectory would still be quite okay. I mean, it would not be as good as these 2, but it will not be disfavored. So it will still be good. So the distribution would shift slightly differently. Much less. And the associated problem is called the variance. So the variance of the gradients in policy gradient. And it basically, you can imagine it as basically if you always have some gradient into, like, that could be, for example, from similar to, for example, these rewards. So in one case, we could have something like 2 small positive values and 1 negative value, or it could be like this, where it would be much smaller difference between the 2, and one would be preferred over another, but all of them would be equally accepted. And in general, this is a better approach. So when we have like less variation in the absolute values of these, or in actually the values of the rewards. So this is something that that is usually addressed in the kind of subfield called reducing the variance. So basically here we have the expression for the gradient as we had before, and one of the way of reducing this variance, reward variance, is the causality. Because if you look at this expression, there is something like fundamentally wrong with it. And the thing is that causality tells us that policy at time t prime cannot affect the reward at time t, which was before the t prime. And that makes sense. So when we take a sequence of actions, when we take, for example, the next action, we cannot, it cannot affect the rewards at the previous, at the earlier time steps. And this will be more clear if we write it like this. So basically, instead of summing for each trajectory, we sum this product. We basically put this, well, basically move the sum. So here for each trajectory, we took for all time steps, multiplied this sum, which we got like a gradient, grad log pi. And this is the total reward for the trajectory. So we multiply this sum by this sum. But now actually, if you move this sum out of these brackets, it would be the same. So basically, we just calculate it slightly differently. So for each trajectory, for each time step, we basically sum this grad log at this time step, and then multiply it by this whole product here. So this is the same expression. We just we changed the way how we sum things. And now this looks weird because for each trajectory, we look at each time step. And for each time step, we have the gradient log pi. So something that describes how our policy should kind of should change. And we multiply it by the sum, again, along the same trajectory, but the sum at different time steps of the reward. And here there is a problem that basically if we have infinite samples, you can actually show that this will not be the problem. So basically all these rewards that we consider at the later time steps, the rewards for the earlier time steps, they would kind of cancel out in many different trajectories. So basically, if we take proper expectation value, there is no problem. So mathematically, you can show the duration is quite complex, but you can show that it doesn't contradict the causality. But in case of a small number of samples or like finite number of samples, this is a problem because at each time step, we look at the rewards that we'll get in the future, which makes sense, the present, which also makes sense, but also in the past. So at some time steps more than one, we will still be using the rewards at time step one. And in a simple way, it's solved by replacing one with t. So basically, for each time step, we calculate the gradual policy, and then multiply it by the sum of rewards from now on. And this part, from now on, is often called reward to go. So that's something like basically it's denoted with a Q because it's kind of similar in spirit to the Q function, but it's not exactly that. And we'll talk about it slightly a bit later. So, but yeah, this function is called reward to go, and this is one of the ways to reduce the variance. So basically, to remove the influence of the rewards that shouldn't really influence us at the current time step. Another way of reducing variance is the baselines, and the simple. We'll just glance shortly through this. Basically, the idea is that if you think about market decision process, if you add the same constant to all the rewards or remove the same constant to the rewards, it shouldn't change anything. It doesn't change the maximum over the rewards, right? And here, for example, if you add or subtract some constant value, the question is, does it change anything? Does it like can we subtract something here to reduce the variance? And for example, like what we subtract would be like the average reward to kind of bring the rewards to distribution with a to slightly different distribution, where some average reward would be effect of 0, and better rewards positive, the negative, the worse rewards than average would be negative. And basically, if you look at this value in terms of expected value, you can actually see that this part doesn't change anything. So basically, when you basically open the brackets here and turn it into the previous equation here, minus b times this, basically in terms of expectation, this integral would be 0. It's quite easy to show because it's basically using the same log trick here. We replace p grad log p with grad p, and then we move the gradient and the constant b in front of the integral, and the integral over the p, which would be the probability distribution of the trajectories. The integral is 1 because it's the probability, and the gradient of 1 would be 0. So basically, in this equation, we can add or subtract some kind of constant value, which, for example, could be the average reward. It's not the most optimal thing to do, but it's quite good in average. And this trick also reduces the variance. So we wouldn't prove it here because it's quite involved, but in general, you can try to solve by trying to write the variance of this value by a very known expectation expression. So this would be like two kind of the first go-to methods to reduce the variance and kind of improve your policy gradient algorithm. Another very important thing to talk about is the on policy versus off policy. So by default, as we already mentioned, the policy gradient is on policy because every time you need to draw new trajectories from the new policy. So, and that makes sense because, here you sample it from the previous policy, and in order to improve the policy, you need to basically use the gradient. You can't use the gradient from a different point, right? So you need to use the gradient from the previous point, and then the next gradient step from the current point, and so on. So that's pretty trivial. And the question is there a way to mitigate that somehow? So can we somehow turn the on policy gradient into off policy gradient? Well, if we look again, to calculate or evaluate the estimated reward, we need to draw samples from the probability of its trajectories given our policy, so current parameters of the policy. And the big question for the off policy algorithm, can we reuse the same samples, or like if we don't have the samples from the most recent policy, can we have samples from another policy, let's say the policy that we had 10 steps ago? And the answer is actually yes. So if you're familiar with the importance sampling, then you know that you can actually, there is a way, if you're given the example 1 distribution, and you want to basically get the expected value of some function from given this distribution, you can actually change the distribution. And the duration is pretty simple, but basically just to sample from a different distribution, you need to multiply your function by the original distribution that you want to sample from by the distribution that you actually sample from. So it's a pretty neat trick. And especially it's important here because it will actually save a lot of resources. It's nothing bad with on policy algorithms, but in some cases it's much easier, or like the simulations could take a long time. So sometimes it's easier to push for off policy algorithm. So yeah, basically to mitigate this issue, we can take some old policy and some old distribution corresponding to that policy, and just calculate the estimated value of this expression. So we multiply our rewards by the ratio between the probability distribution of the like at these points now. And if you write out again this probability distribution according to the equation that we originally had, you can see that they have many things in common, and the only different thing is basically the policy or the probability distributions of actions given states for different policies. And this is something that we can also easily calculate. It's a product, so it's pretty easy, and it doesn't really affect that much the gradient calculation. So, and to finish with a very short note, sorry, we are a bit too late, is the actor-critic algorithms. And I think some of my colleagues will be talking about actor-critic algorithms later, so maybe if something is not necessarily here, they will augment it in their lectures. But basically, the actor-critic algorithm is a combination or like a mixture between the value-based algorithms and policy gradient. And the difference is that here in this step, instead of just estimating the returns according to our policy, we will take the value-based methods approach, is basically take the B function or Q function and approximate that, for example, with a neural network, and use that information to backpropagate into the gradients. And the actor-critic algorithm itself is coming basically from the question is how to improve the policy gradients. And if we here recall that reward to go part of the gradient expression, so you remember we replaced the summation from over the entire time to only look at the future and the present instead of past. And this is something resembling the Q function. So what this function is essentially is the estimate of the expected reward if we at state SIT, so state at the time point t in the trajectory I, if we take action A or AT. And the question is, can we get a better estimate? Because it's an estimate of expected reward, but here it's just a sum. So can we somehow get a better estimate? Because again, don't forget that this i's means that we just sample from the policy. So that means that's not really the best approach to the estimation or the estimated value. And like to think about it, what do we do? Like if we take the trajectory and we take some point t of this trajectory, basically what we do here is we just sum together these rewards. So that's what we do here. So we have this trajectory. We took some point t here, time step t, and then we sum these rewards along the trajectory. So that's Q hat, the reward to go at this point. But actually, like since we always have some probability distribution, both could be like in dynamics and in our policy, actually it could be different trajectories if we start from this state. And this uncertainty should be somehow counted, because now we just take one single trajectory, as there basically could be infinite some kind of distribution of possible trajectories. So we can actually improve this part. Although we got this derived from basically sampling, we can kind of go back and attempt to make it closer to the estimated value instead of just sampled through n trajectories. So essentially what this Q function approximates is the estimated value of the sum of the rewards, or like basically sum of the estimated rewards of states given different states. And the true expected reward to go again would be an expression like this. So instead of just having one sum, we would have some estimated value according to the distribution according to our policy. And the question is, can we, for example, use baselines to help us here? And the question is, the answer is yes. And basically, one of the ways how to do this is basically we again approximate it as a Q function at SIT80 minus something. And this something, again, could be something like average Q function. But then if we look at the basically the value function expression, it is something similar. So it's basically the value function at state st is basically the estimated value of the Q function given current state st and the action at, which is drawn from our probability, from the probability distribution given our policy. And that means that essentially we can use the function value instead of this b constant here as kind of a better estimate of the average Q function. And again, here, this difference is again the advantage function. So the function tells us how much better certain action AIT, so something that we sample is better than the average reward. So the average action. So the entire expression would look like this. So now we have grad log pi policy as before, but now instead of just the sum of the rewards along the rest of the trajectory, it will be the advantage function at this state and this action. And again, so since now we have this advantage function, which, as you remember, can also be expressed to the value function, we can borrow the methods to approximate the value function. So again, if we look at the value function here, for example, for one trajectory, it will be just approximately the sum of the rewards along this trajectory. And if we take n different samples, it would be an average of this. And the question is, can we actually do this sampling? Because if you think about it, so you have state, and then you somehow need to run or get different trajectories from the current state. And this is an important point because, for example, if you interact with the real system, you kind of are forced to work with only one trajectory starting from one state. Because whenever you started from one state, took some actions, you're already in a different state. And for example, in the simulator, you can always reset the state. But if you work with the real system, you cannot reset the original state. So the question, like when you think about what method to use or which formulation to use, this is something to be taken care of. So, and the actor critic algorithm just plugs in the value-based method as, for example, in a neural network or something, a learnable function, and plugs it in the policy gradient. So basically, first you sample some, and it's a batch actor critic algorithm similar to online learning algorithm. So basically, we sample just a pair state and action from our current policy. We kind of unroll this and fit the value function for this S. And then we, again, evaluate the advantage function, plug it into this expression for the gradient, and then we update the gradient and sample it again. And again, the online actor critic algorithm would be basically taking instead of just sampling the pairs of state action from our policy, we can just take some current state, take action given our policy, take the next state, and then do the same trick as we did before, where we basically just did sampling these tuples S, A, S prime. And then again, if you remember the expression for updating, bootstrapped update of the value function, you can update it given the new SAS prime information. And then again, you can evaluate the advantage function, put it into the gradient, and calculate the gradient. So this is very, since we're very short on time now. So this is very crash course into this type of algorithms. But I think we'll be talking about their applications in the future lectures. So if something was important was missed here, we'll augment it there. So thank you for your patience. We took a bit longer than we expected. Sorry about that. And yeah, so are there any questions on that?